In previous videos, we have seen that visible light is an example of an electromagnetic wave. Now, a general characteristic of all waves is that they propagate through a medium. Propagate is just our fancy physics word for travel, right? Waves are traveling. They are transfer of energy without a transfer of matter. So if they're going to transfer something, they got to move. So waves propagate through what we call a medium. It's just whatever substance the wave happens to be propagating through. For the case of mechanical waves, the medium is actually critical to the transmission of the wave itself. Think of a wave on a rope. Like if you take a rope, tie off one end and shake the other end up and down, a wave travels down the rope. Well, the medium of propagation in that case is the rope, and if there were no rope, there wouldn't be a wave. Think of the sound that's hitting your eardrums right now. If it's propagating through air, if there were no air, if we were in a vacuum, the sound wouldn't propagate. Sound can propagate through other things like wood and steel and water. But if there's nothing, the sound can't propagate. EM waves are not precisely like that. They do not, their propagation doesn't necessarily depend upon the medium. They don't use the medium as a means of propagation, but they still propagate through a medium. Right? You're watching this on a computer or a phone screen, which is producing light, which is propagating through the medium of the air to your eyeballs. Light from the sun propagates through a vacuum and then propagates through our atmosphere. So they're going to travel through something even though they don't need the medium to propagate like mechanical waves do. But with that said, we know a couple things about waves. Number one, and we know lots of things, I'm going to give you just a couple. At any boundary between media, right? Medium 1, medium 2. In the case of the sound wave hitting your ear, it's traveling through air, but then when it impacts your tympanic membrane, it changes media to your tympanic membrane and then the fluid that's on the other side of it. So the sound travels through both of those media. So if there are two different media, there is a boundary between them just necessarily, right? There's something here and then there's something over here and there's a boundary between them. So at any boundary between media, a wave, and I'm going to write in general, reflects partially. That means at least part of the wave is going to reflect from that boundary. If you don't believe me, hold your hand up in front of your face and talk. You will hear an echo from your voice bouncing off of your hand. Just 2 seconds, I'm going to get the cat out of the room. Now, when I say in general, that means that there are some exceptions to this. But number 2, I'm going to say the same thing. At any boundary between media, a wave in general transmits partially. That means that part of the wave passes into the new medium. So what I'm saying is a certain percentage of the wave is going to reflect, a certain percentage is going to be transmitted. In some cases, 100% reflects and 0% transmits. In other cases, 100% transmits and 0% reflects. It depends on the wave, it depends on the media, it depends on the conditions. But in general, we expect both of these things. You know, like I said, the percentage that does whichever one could be 100%, it could be 0. But in general, we expect both of these. All right, we're going to take these two ideas into our discussion of optics. So the first thing to do with optics, which is the study of how visible light interacts with objects, and specifically mirrors and lenses, the first thing to do is take these two ideas which came from looking at waves and keep the ideas but forget that we're dealing with waves, which is kind of a strange thing. But as it turns out, light waves have really, 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 really small wavelengths, tiny wavelengths. As it also turns out, another property of waves is that if they interact with objects that are much, much, much larger than their wavelength, their wave properties are minimized. There was actually a debate that raged in history for a couple of hundred years over whether or not light was a wave or a stream of particles. We know now, spoiler alert, that it's both, but for a long time, lots of people denied that it was a wave, Isaac Newton among them, because they couldn't see wave characteristics. And that's the case because light has such a small wavelength, and everything with which we see it interact is much larger than the wavelength. So if we're not going to consider it to be a wave, how are we going to consider it? Well, we're going to consider it to be what's called a ray. And just from geometry, if you think back a little bit, a ray looks like this. We also use the same symbol for vectors, right? But this is a ray, and you've all heard the phrase ray of light, and that's typically how we're going to consider light when we're dealing with what we call geometric optics. That is to say, when we deal with light interacting with objects much, much larger than its wavelength. We're going to think of it traveling in a straight line, as rays do. If it interacts with a boundary, we're going to think of it reflecting, which, remember, is a wave characteristic. But we're going to take that forward, even though we're not considering this as a wave. We're going to remember that it still reflects. So if it interacts with some boundary, we're going to let part of this wave be reflected and maybe part transmitted. All right, so the wave itself, the initial wave, will kind of split. Part of it will be reflected, part of it will be transmitted. And I have drawn these at angles purposefully. We'll talk about that as we go along. But first, let's get some terminology out of the way. If a ray is striking a boundary, as in this case, in the case of light, we would say it's shining on this surface. We say that it is incident upon the surface. We've already gotten the idea of reflection, and we intuitively know what that is because most of us get ready looking in a mirror. The light, notice, is transmitted, so we have transmission, but there's another word we can use with the part of light that's transmitted, which is this word refraction, which basically just means bending. And so we need to talk, we're going to talk about this more extensively when we get to that section, but let's just briefly go over it now. What I said was the rays travel in straight lines and they don't bend. That's true. We're going to let that be true as long as it's in the same medium. But what we will see, and what we can see from this drawing, that the part of the light that moves into a new medium, that is to say the part of the light that is transmitted, can, in most cases, bend in the new medium, right? It's coming this way and then it's going slightly up. This is not a surprise to you if you've ever dropped a pencil into a glass of water and seen that the pencil looks broken. It's not really broken, but the reason the pencil looks all cattywampus when it's in a glass of water is because the light has bent like this. The rays are now traveling in a slightly different direction than the original rays as they cross into a new medium.